For over 40 years, space electronics has specialized in the measurement of static balance. We started out measuring satellites and rockets, and we developed technology that was able to detect extremely small changes in moment. More recently, we've been adding another product to our line which has become very important, and that is the measurement of the static unbalance of jet engine turbine blades. These machines are called moment weight scales, and basically the process is to hold the blade in a very precise fixture and then measure the product of the weight of the blade times the distance of the center of gravity to the center of rotation of the turbine blade when it's rotating in the engine. And if you can come over and look over my shoulder, I've got a drawing that illustrates the process a little more clearly than I can just say in words. This is an illustration of a single stage in a jet engine. We've drawn this particular stage with blades that have a central pin and hole to support them, but in general the blades would be either dovetail or fir tree design, so that the blades would fit in a slot in the rotor. When we're measuring the moment weight of the blades, we're measuring a quantity that's, I said before, equal to the weight of the blade times the distance between the center of gravity and the center of rotation of the blade. This quantity is a measure of the static unbalance of the blade, and it relates to the amount of unbalanced force that will occur when the blade spins at its speed, which might be as high as 9,000 RPM. By measuring all the blades in the set initially and then sorting the blades in the most desirable order, it's possible to match blades so that blades of equal static moment are placed opposite each other and counteract each other in terms of unbalanced moment. More sophisticated programs available that also compensates for the rotor hub unbalance. This is a Space Electronics model mw900 moment weight machine. We've got it set up with an adapter that fits a dovetail blade. The display here indicates the moment in ounce inches. If you've been using a moment weight machine in the past, you may notice something about this machine which is unusual, and that is that the display indicates the moment to the nearest hundredth of an ounce inch rather than the nearest tenth of an ounce inch. And the reason we do this is because of the incredible accuracy of this machine. Expressed in terms of full-scale moment, this machine has an accuracy that is typically about 2 parts per million. So I can place this blade in the adapter, and the machine will measure the moment in ounce inches. And in this particular case, it's reading a moment of 136.58 ounce inches. I want to illustrate just how repeatable this machine is. I'm going to put the blade in the adapter. Read a moment of 136.58 ounce inches. Now I'll remove this blade, and I'm going to insert it back in the adapter several times, and you can see just what the repeatability is. 136.58. .58. So we're varying less than 0.01 ounce inch on a machine that has a full-scale moment of 13,000 ounce inches. That corresponds to 1 part in 1.3 million when expressed in relationship to the full scale of the machine. I want you to know in all honesty that the previous demonstration which you just witnessed was not a trick. That is the first time that we photographed the machine doing that particular repeatability measurement, and as you saw, the numbers came out exactly the same to the nearest hundredth of an ounce inch. When we first designed this machine and began testing it, we just couldn't believe how accurate it was. We had used technology that was unique, and we knew that we'd be improving the state of the art by a major factor, but we really did not expect to get the degree of performance that we have been getting with these machines. In fact, when we first built the prototype, I used to go out every single day for at least 2 weeks, and I would take a turbine blade and place it in the machine, and much to my astonishment, come up with exactly the same answer every single time. And for many days, we didn't even bother to re-zero the machine. The machine maintained a stable zero over a 24-hour period that was so close that the error in the measurement of the turbine blade was in the order of 1 or 2 hundredths of an ounce inch maximum, even without resetting the zero of the machine. This illustration shows the way that moment weight used to be measured back in the 1950s. The turbine blade is fixtured to a balance beam. The balance beam is pivoted on a knife edge, and there's a force measuring device, a strain gauge load cell, which is mounted at a exactly known distance from the center of pivot of the knife edge, so that the load cell measures a rotational moment about this knife edge. When you place the turbine blade in the adapter that's mounted to the beam, then the force of the blade is downward through the center of gravity. This produces a moment which is counteracted by the load cell, so that you can use this load cell to measure the moment of the blade about the central pivot. There are two features to this machine that are important to its operation. The first one is a counterweight which can be slid back and forth to counteract the moment due to the adapter, so that before you put the blade in the adapter, you can adjust this thing for a zero reading on the load cell. And then if the blade has a moment which is beyond the range of the load cell, you can then add range weights to a pan, which act through a precisely known distance, and add to the counteracting moment so that you can extend the range of this device beyond the range of the load cell itself. Now, I mentioned that this method was developed in 1950s. Amazingly to us, when we first got into this business in the 1980s, we discovered that all of the moment weight machines that were being sold still used the old technology. It has a number of serious fundamental drawbacks. One of them is that the knife edge pivot has to be so narrow that it is very fragile. It has to be probably 20 or 40 millionths of an inch wide in order to achieve the accuracy you need for modern moment weight specifications. And obviously a edge as sharp as that will break down almost immediately under repeated use in a production environment. And the second limitation of this device is that the strain gauge load cell is a device that has a very limited dynamic range. You're basically deforming a piece of metal near its elastic limit and then measuring the strain in this piece of metal. The higher quality load cells have a dynamic range of approximately 1 part in 2,000, which you can enhance a little bit but still stay in that same order of magnitude. This is not anywhere near good enough for modern requirements for moment weight. Here's an illustration of the basic concept used in many of the space electronics moment weight machines. The technology which we use was developed originally for the space program, where it was essential that the center of gravity of satellites could be measured with accuracies approaching 1 part in 100,000. So first of all, rather than using a knife edge pivot, we have a cross-web flexure as the central pivot. Cross-web flexure is a series of blades of spring steel that are oriented in such a way that the effective center of rotation is right in the center of the pivot. But unlike a knife edge, it does not wear, it does not break down, it retains the same degree of precision year after year. This technology was originally developed by the National Bureau of Standards for use in their primary standard calibration systems, and we've extended this technology to moment weight machines. The moment itself is measured by a force restoration transducer, which is a device that applies a moment which is equal and opposite to the moment created by the turbine blade. First of all, this means that the system returns to its original mechanical position. When the blade is mounted on the machine, the arm momentarily deflects a very small amount. A laser beam detects this deflection, and then a force is applied to bring the beam back to its original condition. And by doing so, we eliminate all of the mechanical nonlinearities of the system because we have essentially nulled it out to its original position. Secondly, though, the device itself, the force restoration transducer, is operating at a very high voltage. Instead of having a signal in the order of 5 or 10 or 15 millivolts, we have a signal which is 5 or 10 or 15 volts. So we have 1,000 times better signal-to-noise ratio than a strain gauge load cell. You combine these two features together, and this technology gives us the incredible accuracy of 1 or 2 or 3 parts per million. In order to make use of the extraordinarily high accuracy of this moment weight machine, we need to be able to support the blade in the machine with a precision in the order of 100 millionths of an inch. We have a unique fixturing method, which we are applying for a patent, that holds the blade with this precision without requiring any movable parts. Basically, this adapter cradles the blade in such a way that the force of gravity applies an outward force to keep the blade extended so that it contacts the adapter at what's called the Z-plane of the blade, and at the same time the tilted design of this fixture causes the blade to move sideways against a stop that provides alignment of the blade to duplicate what position the blade would have in the engine when the centrifugal force pulled the blade outward and caused it to extend directly out from the mounting slot in the rotor. I'm going to take the blade out so that you can see the process once more. There are 2 round rods that are spaced in such a way that they contact the Z-plane of the blade at exactly the same point as the blade is contacted in the engine. There's a wedge mechanism at the bottom which forces the blade toward these pins when the blade is fully inserted into the adapter. And then we have a stop mechanism that contacts the blade at right angles to provide the alignment of the blade in the adapter. It's been at least a half an hour since I gave the demonstration of how repeatable the blade measurement was with this machine. First thing you'll notice, I have not reset the zero of the machine, but it is still exactly on 0. Secondly, and now I hope this is going to be a value similar to what we had before, I'm going to insert the blade in the machine, and now we read a value of 136.58. I'm hoping that you remember the value that we had before, which was, whoop, it just changed, It was 136.58, and now we have changed by 0.01 ounce inch. And as you can see, since it went from one value to the other, it's possible that we were straddling the point between those two digits. So we are still measuring the same blade with an accuracy of approximately 1 part in a million. Different turbine blades will require different length adapters to be mounted on the moment weight machine. It's necessary to counterbalance the tare moment of these adapters so that we can make use of the full range of the machine. This counterbalancing is accomplished by moving the sliding weight on the front of the machine. It's a very easy process to adjust this counterweight because we have a bar graph on the display. This bar graph has a highlighted red area which indicates the optimum position for the tare balance. The operator can adjust the weight until the blue line, which is the true measured moment, falls within the desired region so that we get the full range of measurement on the moment display. In addition to the counterbalance weight, we also have range weights that can be inserted onto a hanger that's mounted at a precise radius relative to the measurement beam in the moment weight scale. The computer has a feature built into the measurement program which allows the operator to key in the number of range weights that he's added. And once he's keyed that number in, then the display will automatically update so that it indicates the total moment. Because of the extremely high accuracy of this machine, we had to develop a new method to calibrate the machine. Traditionally, moment weight machines are calibrated using rods and cylindrical weights or using a knife edge and a hanging platform. But neither of these methods would be acceptable for a machine that has an accuracy that approaches 2 parts per million. So what we developed is extremely simple, but also very elegant. The calibration system consists of a perfectly round ball that has been machined to a very high tolerance, and a cavity that has 2 surfaces whose distance has been determined with an extremely high degree of accuracy. The ball is placed in the calibration fixture, and because of the shape of the bottom of this fixture, the ball rolls against one side. The machine then measures a moment, and we press the enter key on the machine to accept that moment. And then I roll the ball to the other side of the cavity, and again the shape of the cavity causes the ball by gravity to press against the opposite surface of the cavity. And then I press the enter key on the computer a second time. The computer now takes the change in measured moment and compares it with the true moment and automatically adjusts the calibration factor of the machine. There's no need to turn threaded weights. There's no need to set gain dials. Everything is performed automatically through the built-in computer in this instrument. The value of the calibration moment in the instrument is easily traceable to NIST because all we need to do is measure the weight of the ball, the diameter of the ball, and the distance between these 2 surfaces. We subtract the diameter of the ball from this distance and multiply it times the weight, and we have a number equal to the precise moment change for this calibration fixture. And then finally, if we want to determine the radius of the mounting plate on this machine, by placing the ball at this end of the machine, we have introduced a known mass at a known deflection from this mounting surface, and so mathematically we can determine the radius of the machine itself with an accuracy in the order of 100 millionths of an inch. In addition to the moment weight machine which I demonstrated, we make several other sizes of machines with different features. Our smaller machine has the capability of measuring the pan weight, or in other words, the weight of blades, as well as measuring moment weight. We've provided this feature because in some facilities, very small blades are not moment weighed, and calculations of unbalanced are just based on the pan weight of the blade. We have a larger machine which has a full-scale moment of approximately 20,000 ounce inches and measures moment weight along all three axes of the blade. Two of the axes are measured simultaneously, and the third axis of measurement is obtained by rotating the blade 90 degrees in a rotary table that is built into the machine. Our larger machine also has a unique feature. There's an auto-ranging mechanism in the machine that adds range weights to the beam without having to handle these weights personally. The mechanism itself lowers the weights in a binary order in order to achieve increments of moment until the correct moment is obtained. I'd like to invite any of you watching this video to come to Space Electronics and witness a demonstration of one of our machines. We're very proud of what we've accomplished here, and we want to share it with you. The previous video you've been watching was made several months ago, and since that time we've had a chance to show it to a number of people and get their comments. And I think people were pretty interested in our machine, but they had some questions, and I'd like to try to answer them right now. The first question they had was, we basically demonstrated repeatability, but what is the accuracy of the machine? And the second question really was not so much a question as an observation, and that is the machine is so repeatable that it's almost hard to believe. So what I'd like to do is give a demonstration, first of all, of what we might get as an answer if we were to take a totally different moment weight machine and measure the same blade using the same adapter. Now, I don't know if you remember the value that we were getting on the mw900 machine, which had a full scale of about 13,000 ounce inches. That value that we were measuring was 136.58 ounce inches. Now for this demonstration, we have a model mw900 machine, which has a full scale of 900 ounce inches. And I'm going to put this blade back into the same fixture, and we'll see what moment we measure. And it looks like we're getting 136.58 ounce inches, exactly the same value that we got with the other machine. In order to illustrate the variation in moment weight reading, I'm going to change the resolution of the readout so that it reads to the nearest 1,000th of an ounce inch. First I select the setup menu in order to change the configuration. I go into the units mode and I have to type in a password. This password is required so that a machine operator won't inadvertently change some of the critical parameters of the measurement. And then I can scroll down until I get to the number of digits beyond the decimal point, and I'm going to change that from 2 to 3. And then accept that change. And now I'll exit the setup mode and go back into measurement. And now what we're observing is a more precise moment. Instead of being 136.58, it's 136.577 ounce inches. And now we can see even more precisely what the true variation is in reading. First we observe that the 0 point is actually drifted by 1/1000th of an ounce inch. If I want to, I can reset that 0 so that it's exactly on 0. We're now dealing with such small variations that if I bump the machine when I do that, then it gives me a slight error. And then I put the blade in. And now we're reading 136.580. Let me do several of these to see what the variation is. I'm not going to change the 0 setting, but just reinsert the blade. 136.580. Here's another measurement. On 36.581, but you'll notice that we're not going exactly back to 0. On 36.581, so we're varying just by luck less than 1/1000th of an ounce inch. But the reading is not exactly valid because the 0 point is not right on 0. It's about 4/1000th of an ounce inch off. I'll do another measurement. .136.50, so it's changed by 1/1000th of an ounce inch. So when we get down into this resolution, now we see some very small effects. If the temperature were to change by a few degrees as we made this measurement, we would see the moment change. And here you can see the machine does drift in the order of 1/1000th of an ounce inch. Once again, I'd like to extend an invitation for anyone who's watching this video to visit Space Electronics and see one of our moment weight machines firsthand. I'm happy to see that the machine, even though we've been setting this video up for a few minutes, is still reading 136.58. And we probably will be keeping this blade and this adapter here, so if you come to visit us, you can make the measurement yourself. Thanks for watching this video.